Okay, camera movement. So we do have this MVP, right? Model view projection. And we calculate this matrix only from projection and the model. So if you remember, the projection actually translates world coordinates into clip space coordinates for rendering, and the model just moves the model and rotates the model that we have, and this V stands for a view, of course. So what we need to do is add a view matrix here, and this view matrix will be controlled by our camera, right? So let's just start with that. We would say something like view mat, and for now we can actually have an identity matrix, so it has no effect. Something like matrix for F32 identity. So this would be a matrix that does nothing. We just need to put it here in the middle, right? Because MVP. So what will happen is that first, whatever coordinates we have will be transformed by the model matrix, then that would be transformed by the view matrix, and finally that would be transformed by the projection matrix into a clip space. So far so good, nothing has changed, that's good. Now what we basically want to do is calculate this matrix from some camera, and we need a way to represent the camera somehow. Well, the most common way to represent camera is actually by having a position of the camera and the target position at which the camera looks, right? So we can simply define it as another variable like this, camera, and that would be a structure that would contain a position of vector 3, right? And then the target. And now we can take this camera, and here we can calculate the view matrix using one of the linalc functions like this, linalc matrix for look at. So there's this F32 version, right? And that would take an I, which would be our camera, right? The position we are looking from, so that would be camera position. Then the center, that would be the center of the target at which we are looking, that would be our camera target. And finally the up vector that is needed for calculation, that would be our up vector, which is a vector that points up to the y coordinate, exactly like we use here for rotating around the y-axis. And this optional flip z axis argument, which is true by default, basically controls whether a negative z is forward or back. And by default it's true, that means that the negative z is forwards, and this is exactly what we also specify here for the projection matrix, so this needs to be consistent, right? Now we can actually move our model at the origin, for example, right? And then we can initialize our camera, maybe in the init function, for example, with some positions. So let's say that a position of the camera is a little bit behind the tractor, right? So if our tractor is at the 0 coordinate at the origin, then the camera could be like 3 meters behind, right, to the back. And the target, that could be just a 0 vector, right? So that means that the camera stays 3 meters back from the origin and looks at the origin. Let's see if that works. Yeah, looks good. Well, since our camera is at the 0 y coordinate and it looks at 0 y coordinate, and the mesh origin of the tractor is actually also at the 0 y coordinate, right? It seems like we are looking at the floor, so maybe it would make sense to actually have some kind of eye position to have a slightly higher point of view. So let's just do something like eye height or something, and we can say that this is, I don't know, 1 meter. We are not very tall, and now we can just put this here, so we are like 1 meter above the origin, and we are looking also at 1 meter above the origin point. So now it looks pretty nice, right? So now what we need to do is basically just modify position and target from our input. So how do we do that? Well, we need to introduce some function like update camera, and this function will need a delta time because it will update every frame, and to be smooth and frame rate independent, it would of course need the time passed since last frame. So this is what we are gonna implement now. Let's write the procedure, simple as that. That takes of course our delta time, like dt. Now what do we need to do here? Well, we need to get move input, calculate movement direction, calculate motion, apply motion to the camera position. And finally, because we are implementing a simple first-person view camera, we also want to update where we look at, right? We always want to look at some point that is relative to our position. So we need to update camera target. So to get the move input, we will use the keyboard input, so like WASD. And later for the mouse look, we will also use the mouse, right? So how do we get the move input? If we take a look here at our poll event, we are actually already handling a key down event, right, for our escape. So we check if scan code is escape, then we just break the main loop and exit the program, right? But what we could also do in this event handler is record which key is down, and then we could also add the handler for the key up event to set that the key is not down anymore. So we can do something like key down, and that would be a mapping from event key scan code. We would set it to true here, and then we would also have a key up event. Like this, we would just set it back to false, right? Now this key down can be a simple array in Odin, which actually has enums as an index. I think it's called enumerated array in Odin. So we can define this as another variable like this, something like key down, and the type for that would be an array of Boolean, but we can also specify the indexing type, and that would be SDL scan code, like this, right? Now Odin will actually complain that the enumeration is not contiguous here, and it can be used like this for an indexing array. And the reason for that is that the values here that we use, they don't go from 0 to the number of actual elements in the enum. They have some other values, like for example, we have here a reserved value of 400, and then 511, right? And before that we have 290, and overall the number of elements is not the same as the maximum number of elements, which basically means that this sequence of elements is a sparse array. So the actual array to store these indices will be more than the actual amount of the options, but this is fine. It will be just 520 bools, so it's not a big deal. So we can do exactly what Odin suggests here and prepend the sparse here, right? So we would just say sparse. And now here in our update camera method, we can start with just logging some key codes, right? So let me just log debug key down W, right, for example. So you see it's false, and now I'm pressing W, it's true. Now I'm not pressing, it's false again, it's true. So that seems to be working fine. Now SDL actually provides this function called getKeyboardState that we could actually use as well. And what this does is also returns an array of Boolean, and it's also indexed by the scan code here. So what we could also do is basically just call this function and assign the result to our key down type like this as a sparse scan code array, and that would work as well. But I think it might have some benefits to have more control over the actual key down and key up events for later. But you can also use the get keyboard state, of course, that should be no problem. Now back to our camera main function. What we want to do is construct a move input out of keys that we press, right? So let's define our move input as a vector 2. And then we simply say if key down W do move input. Well, let's say that y-axis will be our forward and backwards, and the x-axis will be left and right, right? And forwards will be +1 and backwards will be -1. And for the horizontal input, we will say that left is negative and right is positive. So we'll just say this is 1. So otherwise, if W is not pressed, we say if S is pressed, then we say that key down is -1. And then we do the same for horizontal input. So we say A and D. So A, that would be to the left, -1, and X coordinate, and then D to the right, right? Now what we can do is actually log the move input. So now I'm pressing W and we have Y1. Now I'm pressing S and we have Y -1, A for X -1, D for X +1. So that seems to work fine. So this is done, we have the input. Now we want to calculate the movement direction, right? So the movement direction would be how much do we move forward if we press W or S, and how much do we move right or left if we press A and D, right? So that would be basically a combination of two vectors. So let's say something like move direction forward multiplied by move input Y plus right multiplied by move input X. Now, how do we get this forward and right? Well, this will be our view direction, like look direction, but since we are not implementing mouse input just yet, we will just use the absolute world forward and right vectors. So that would be forward vector 3 of 0, 0, -1. Remember that -z is forward, then right is vector 3, and that is just 1 by x, 0, 0. So this is our movement direction, and it will be multiplied by our movement input, right? Now if we actually log this, you can see that it is 0, and if I press direction keys, it gives us a 3D vector, right? So far so good. Now out of that we need to calculate the motion, and the motion is basically how much do we move towards the movement direction at this given update time, right? Like delta time. And here is where we would apply speed, like movement speed. So maybe let's introduce a move speed constant. Let's say that we are moving like 5 meters per second or something, and go back, and now we say, all right, our motion is move direction multiplied by speed multiplied by delta time, right? So basically we say move towards this direction by the fraction of the movement speed that depends on the delta time, right? By the time passed since last frame. And this is almost done. Now we can just simply apply the motion to the camera position. So that would be camera position plus equals motion. And then we update the camera target. That would be simply camera dot target. And we want to look forward always. So that would be camera position. So remember, it should be relative. So that means that we just take the camera position and apply our forward vector here. Now if we run, you see, we can actually move. We cannot change the direction yet, but we can move. But this actually have one problem, that the movement direction is not normalized. And that means that if we press both forward and right, for example, so we have one here and one here, so for y and x, we have a vector of direction that is more than 1 in length, which means that we will move faster diagonally. And this is quite a common problem, and thankfully it's very easy to fix. We can just say linalg.normalize our movement direction before we actually applying it. One thing to care about here though is that if we do not press any keys, this will be 0 vector, right? And normalizing a 0 vector will give us garbage, because to normalize a vector you basically divide it by the length, and you can't really divide by 0, right? And have sensible results. But thankfully in linalg there's a handy function that is called normalize 0, which simply does the check, like if the length is 0, then it just returns 0, which is exactly what we want. So now our diagonal movement is of the same speed as the normal movement, and we can proceed to actually changing the direction via the mouse look. Alright, for the mouse look we want to basically modify this forward and right, because our target depends on the calculated forward as well. And how do we do this? Well, we need to collect the mouse movement since the last frame, right? And for that we can use a mouse motion event. So case mouse motion, and this will give us motion data. So in f.motion we have xrel and yrel here, right? This is the relative motion in the x and y direction, so in pixels basically how much the mouse has moved when this event was captured, right? So what we want to do is accumulate over the frame and then use this information when we update the camera. So this will be some value per frame. So let's maybe just have another variable called mouse move or something, and that would be just a vector of 2 because we need x and y. And now what we simply want to do is accumulate it like this. So mouse move equals f.motion.xrel and yrel, right? And even if we have multiple motions during the frame, this will be accumulated. One thing that we need to do as well is, of course, set this value to 0 at the beginning of the frame. So next to our allocator, what we want to do is just set it to the default value like this, right? We could also set it to zeros like this, but in Odin you can just do this, right? This will be default value. So now if we go to the update camera, we can actually log our mouse movement, like debug mouse move, right? And try to see. You see we are getting this delta, and if I'm not moving the mouse it's 0, if I'm moving it's some values. So far so good. And what we want to do is have some kind of player look information that consists of yaw and pitch, and we will change this yaw and pitch depending on the mouse move. So we want to collect this into our look angles basically. So let's also introduce another variable for that, something like look struct that has a yaw. So basically our heading, our horizontal rotation, and pitch, which would be our vertical rotation, so around x-axis in 3D space, right? So this will be 0 by default, that's fine. And now what we just need to do is get the look input, update look values, and calculate forward and right vectors. So how do we get the look input? Well, we just say look input is basically our mouse movement maybe multiplied by look sensitivity, because we want to control this, right? Yeah, this topic is a little bit tricky because like the mouse movement can be different depending on the actual device setting and whatnot, but the easy solution is just, you know, introduce a look sensitivity, which is just a multiplier to the mouse movement. So that's what we are gonna do. Maybe just add it here. Let's start with 1 for now, and that would be our look input. And what we want to do now is update our yaw and pitch. So let's start with yaw. We say look.yaw. That's gonna be our current look.yaw minus mouse move x, so the horizontal movement. Why minus? Well, because we actually want to invert the rotation angle, because mouse movement to the right will be positive, and the positive angle will actually rotate on the other side, so towards the left direction, so that's why we want to invert it like this. And another thing that we want to do is actually clamp the values so they do not exceed 360 degrees, right? And for that we can use the math function from Odin. So we have math linalc imported. Let's also import just a normal math, and we can now use math dot, actually not even clamp, but actually wrap this value by 360, so it will be always within this range. So this is for the yaw. And now for the look and pitch, we do similar stuff. We say look pitch, and here we can also do plus or minus. That actually depends on your preference, whether you want to have inverted vertical look or not. Normally I use the normal one, so we will do just minus mouse move dot y. And this one we actually want to clamp to like minus 90 or plus 90, so you cannot like do a salto basically with the mouse look. So we actually use math clamp here, and actually instead of 90 we're gonna use 89, or rather minus 89 to 89 to avoid problems with Euler angles, which our yaw and pitch effectively are. That will actually flip our yaw on the extreme pitch values. You can read more about this, and like this common problem, the solution for that would be probably to use quaternions, but this is out of the scope of this tutorial video. So now we can just log our look value. So log debug look, and see how it changes. So I move the mouse, you see it's wrapped by 360 on the yaw, and pitch is actually clamped, so this is nice. These two are done. So basically now what we want is calculate this forward and right vectors. Thankfully that's actually very easy because linalc actually has a handy function called matrix 3, or there's also a matrix 4 version, but we can use the matrix 3 for our 3-dimensional vectors from yaw pitch roll f32 this time, right? And here we just pass our yaw and pitch and roll. Just remember that those should be also in radians and not degrees, so we will use again linalc.to radians and just pass look.yaw and also look.pitch. By the way, instead of using this function, you could also just multiply by linalc.read per dec, or if you want to convert back, you could also multiply by that, so that's just a matter of preference. Anyway, this gives us a look matrix. Yes, that needs a roll, which we don't use, so we leave it at 0. And now what we simply do is basically just multiply this by our look matrix, and that should be it. You see, it seems to be working just fine. There is one issue, is that the mouse is actually not confined to the window. So this is something that we can very easily fix with a special function in SDL that is called SDL set relative set window relative mouse mode, this one, right? And we just pass the window to it, and true. So if we take a look at the documentation for this function, it will say while the window has focus and relative mouse mode is enabled, so which what we do, the cursor is hidden and the mouse position is constrained to the window, which is exactly what we want. And that requires that the results are handled. And this one we can actually simply ignore. With Odin, how you can do this is simply assign to underscore. Now it's here. The sensitivity is a little too big, so maybe we can modify this to 0.3 or something. And now we can try moving around. You can see we are moving just fine. We can even fly. If we don't want to fly, then we could just zero out the movedir.y here. So we basically cancel out all the y, so vertical movement, and the movedir will be normalized anyway after all, so that doesn't change any speed. So yeah, that's pretty nice. Maybe one thing that we could look into is that if we go into the tractor, so into the model, you see that we are drawing a lot of back faces, and this is actually quite inoptimal. So this is something that we can change in our pipeline setting. So if we go to setup pipeline and open our graphics pipeline creation information here, you see there is a field called rasterizer state. And that has a bunch of options, like how do we want to fill the polygons. So that could be like a proper fill or only a line fill, so like that would be just wireframe. But what we are interested here is the cull mode. So by default it's no culling, but you can cull front or back faces, and we want to cull the back faces. So let's just write rasterizer state, then specify the cull mode. That would be back. And now if we go into the tractor, you see that a lot of faces are not rendered from the outside. So this is just an optimization. Now how it actually decides which face is front and which is back is by this front face parameter, which can be counterclockwise or clockwise. And this means that it is important how you specify the order of indices or vertices in your rendering call. So you can experiment with that. And maybe just to show you, we can also say fill mode. We can set it to line and see our tractor in wireframe. Nice. Let's comment this out. Very good. So yeah, hopefully that will get you started with SDL, with some 3D graphics, and I will explore this further. I don't really plan to make any more videos on this topic, but if something very cool, very interesting pops up, I will of course upload a video with my experiments. So stay tuned.